Hey y'all. So I will be recording the second part of the sterilization topic in this session, and the topics I'll be going over are gases, filtration, radiation, and chemical agents that can be used to act against certain parts of the cell. Okay, so the first part I'll be talking about are gases that can be used for sterilization, but they have different, I guess, varying levels because some work better at different temperatures, others may or may not penetrate things as well, and some may be stronger more than others. So anyway, share my screen with y'all. Okay. So I have also ethylene oxide to add to this list, but I just ran out of room, so I'll write that down in just a sec. So for the first part of gases, you have VPL, does not penetrate materials well, decomposes rapidly, and then you also have vaporized hydrogen peroxide. It is used at a wide temperature range. You have chlorine dioxide, and that can be used for high-level disinfection, and I just wrote out what high-level disinfection is, just as a brief refresher. And it's an inactivation of most vegetative bacteria. Remember, vegetative is usually pertaining to reproduction or propagation. And then you have fungi and a 6-log reduction of mycobacteria in its species or subspecies. Chlorine dioxide is also effective between the pH of 4 to 10. And then it destroys biofilm, spores, vegetative bacteria. It also affects proteins, membranes, and nucleic acids. These are probably the two of the most important points here on this slate here. Later on in the session, I will do a drawing. I'll draw a picture of the cell, and I'll write down different groupings of the chemical agents that basically work against or attack against that area of the cell. So it's good to keep this in mind for the gases. And then the second part of the gas, just add this to your list, is ethylene oxide. Okay. So for sterilization, ethylene oxide can be used for sterilization because it reacts with proteins. Can be used on heat-sensitive materials such as food preservatives, and medical supplies. Ethylene oxide also penetrates packaging. And it is affected by temperature and humidity. And I'll give you those specific numbers now. So, can be affected by temperature here with 5 to 8 hours at 38 degrees Celsius, or 3 to 4 hours, 54 degrees Celsius. Now the drawback here with ethylene oxide, it is toxic, mutagenic, and expensive. It also has explosive properties because it cannot, a certain percentage cannot exist in air, or it cannot do more than 3% in the air. Usually 10 to 20% in CO2 or dichloro-difluoromethane. Dichloro-difluoromethane. I'm just putting a dash. I don't know how to And then there's this process of degassing. Once, if you use ethylene oxide for sterilization, you need to do the degassing process to remove the toxic residues. So degassing. Must remove toxic residue after sterilization. Okay. Now on to filtration. I don't know how in depth your professor may ask about filtration or gases, but I just want to make sure I comb through this thoroughly enough in case there is a rather specific question on this. But a lot of these questions may be more of grouping, or it may be like, which the above do or do not do this kind of thing. So if you know the particulars of them individually, then that'll help you narrow down the question or due process of elimination, however the format of your test is. Excuse me. Okay, so filtration physically removes the microbes. Okay. Filtration for heat-sensitive liquids. So the filters used for heat-sensitive liquids are through membrane filters, and there's two different sizes for those. There's a membrane filter of 0.45 micrometers, and then a membrane filter of 0.22 micrometers. There's a filter for air, and usually that filter is the HEPA filter. HEPA stands for high efficiency particulate air. So for the HEPA filter, usually that size, the size of the filter, or like basically the holes within the filter, are 0.3 micrometers. And what's important about the HEPA filter is that it removes particles with 99.97 efficiency. That makes sense though, because if your filters are very small in diameter, so 0.3 micrometers, there's not a lot's going to be getting a lot of, I guess, the wrong kind of particles are not going to be able to get out because they won't be able to get past the filter. Then also, y'all are probably familiar with this, the laminar biosafety hood. We have this in the biology and chemistry labs, and I'm sure y'all have had at least one hood in your chemistry or high school science class back at home. So for the laminar biosafety hood, the laminar biosafety hood forces air through the HEPA filters. And the laminar biosafety hood projects vertical flow of sterile air across CO2. Then finally, we also have the biological safety cabinet. So in the biological safety cabinet, what happens is the room air enters the grid at the front of the hood. Oh, that does not put the word front. So at the front of the hood. And then filter air flows through the grid. And that air is blown up and out through the HEPA filters. Okay, so with filtration, it really depends. Just listen carefully to what your professor prefers or what he or she talks about or emphasizes more in lecture. From my experience, the students really need to focus on the sizes of the filters, whether they're for liquids or for air, and then why the HEPA filter was so important and the efficiency, so 99.97% efficiency. But it varies every year. That was just in my experience, the main highlights that they really needed to know. So the next topic we're going to talk about is radiation. Now I'm just going to pull up this page. So as you all know, that radiation is basically the process where energy is emitted as either particles or waves. And it can, like broadly speaking, it can take the form of heat, sound, or light. But most people usually refer to radiation from electromagnetic waves, which can basically range from radio waves through the visible light spectrum and up through gamma rays. Okay. So now that I prefaced that with about radiation, there's basically radiation can be classified as two types: ionizing and non-ionizing. And I went to this website for my SI sessions to give a visual to the students to show, okay, here's the wavelength, this is non-ionizing, this is ionizing, with visuals for examples, okay? So to determine whether or not a radiation is ionizing or non-ionizing is based on whether it has, like, that energy is able to remove electrons off atoms that it interacts with, and as well as being able to do low energy damage such as breaking chemical bonds and molecules. So ionizing radiation is caused by unstable atoms giving off energy to reach a more stable state. Okay, fair enough. And is more of a health threat to humans because it involves changing the basic makeup of atoms and cells, and more specifically the DNA molecules inside of cells. It does, of course, take a very strong dose of radiation. Okay, so basically, I mean, that's a pretty clean, like, a straightforward definition of ionizing radiation. But then here, with non-ionizing radiation, sometimes people misconstrue the UV light for ionizing radiation because of the damage. Like, if you have too much, basically, it can hurt your skin and cause skin cancer. If you get too much sun and you don't wear sunscreen, all that. And even though, yes, it can create an increased risk in cancer, that doesn't necessarily mean that UV light is ionizing radiation. So most non-ionizing radiation, which is seen here with these examples, it's only harmful up to the amount of heat energy it transfers to whatever it hits. So UV light is quite unique in that while it is non-ionizing, it does have the capacity to cause harmful effects similar to what ionizing radiation can create, such as an increased risk of cancer due to damaged DNA molecules. So I just talked about that. This last sentence is important, such as an increased risk of cancer due to damaged DNA molecules. So UV light damages DNA molecules through the formation of thymine-thymine dimers. And I have an animation that I'll show you in just a sec of like how those thymine-thymine dimers form. But I'll make these notes real quick. And then we'll continue. Let's play with the pen. Okay. So radiation, you have UV, right? And it's non-ionizing. That's a small non-ionizing. Okay. Damages DNA, causes TT thymine dimers. Kind of like whenever you get sunburn, I'm saying that UV light has little penetration, right? Because whenever you get a sunburn, it's just on your skin. It doesn't it doesn't saturate through to to your blood vessels or something like that. Okay. Then other ionizing radiation would be like gamma rays or X-rays. So gamma rays, X-rays, ionizing. Okay. So remember, the ionizing radiation has the unstable atoms. So if they have unstable atoms, then there'll be reactive molecules in microbe. And so the ionizing radiation will affect heat-sensitive materials. And ionizing radiation is measured in absorbed radiation dose. Absorbed radiation dose. So that is indicated as a rad. So there's 100 rads and 1 gray. Okay. So like a dental X-ray would be an example of like 0.5 to 3 millirams, and then like a smoke detector would be less than 1 milliram. So I think this is a helpful page. And then here's the animation I was talking about.
When cells are exposed to sunlight, radiant energy can damage the DNA. For example, ultraviolet irradiation causes covalent bond formation between adjacent thymines on the same strand of DNA. When DNA is damaged in this way, it cannot be replicated or transcribed. Most cells, however, are able to repair damage to DNA. For example, an enzyme called photolyase can break the covalent bond between the thymine dimers. This enzyme requires visible light, which is used as the energy source for bond cleavage. Hence, this mechanism is referred to as light repair. A second repair mechanism involves an enzyme that excises the damaged segment from a single strand of DNA. This process is termed excision repair or dark repair and does not require visible light. The excised nucleotides are then replaced by DNA polymerase. DNA ligase forms the final phosphodiester bond.
Okay. So there's that animation, and since this is a recording, if you want to rewatch it, you can just rewind it back a little bit. Okay, I always played that for the students during the session if they had questions about radiation, or specifically the thymine dimers and UV light. Okay, so now we're going to move on to chemical methods used for the antimicrobial activity of germicides. So we have disinfection, some of the chemical agents used for disinfection can be used for sterilization. It can be used on large surfaces, but they are heat sensitive. Antisepsis. And then preservatives, but they're usually weaker. And with these methods, it affects membranes and enzymes. So now I'm going to look at the handout. This is a very good and organized representation of basically which germicide can wipe out the which bacteria, fungi, or virus. So if you look at the low-level germicide, which would be heavy metals or surfactants are soap, basically. As you can see, the low-level germicide does not wipe out the endospore, does not wipe out the mycobacteria. Other bacteria, it can wipe out maybe some. It's not, this handout isn't super specific on the other kinds. This is kind of focusing on endospores, mycobacteria, the naked or enveloped viruses, or the, and then also the fungi. But then the higher the level of germicide, basically the more that it wipes out across the board. But you just want to make sure, pay attention to these categories here, and that'll help you organize, like, okay, if I use like a phenolic, then it's not going to destroy an endospore. Okay. Now, the thing is, how do you know which germicidal agent to use? So that'll be dealing with selection. And the factors that you consider the selection are the following. So you're looking at toxicity, activity in the presence of organic matter, and whenever I'm saying selection, I'm talking about selection of which chemical agent to use. Compatibility. Great. Okay. Compatibility with material. Cost and availability. Environmental risk. And storage and stability. So this is all what's taken into account for selection. Now, the picture that I was talking about before was this. It's going to be it's not going to be super detailed. My drawing skills are not the best, but it's fine. I'm just pointing to certain structures, so I'm not trying to draw a masterpiece here. Okay. So there's a cytoplasmic membrane, proteins, and DNA. Okay. So I'm fixing to write the chemical agents that can be used to affect these particular parts of the cell. Okay. Some of these overlap, but it's up to you if you want to draw a diagram like this, or if you want to do a T-chart, or just write it in your own way. I recommend that you definitely know the groupings of this. Okay, to know which chemical agent affects which part of the cell, pretty much. Aldehydes, halogens, metals, ozone, oxygens, and phenolics. And here you also have ethylene oxide and aldehydes. So as you can see, aldehydes overlap, and you have phenolics that overlap. Okay. So just make sure that you understand this. Like you can say, okay, here I see phenolics are both that phenolics both act against the cytoplasmic membrane and proteins, but then ethylene oxide really only affects the DNA. Okay. Now I'm going to basically go into detail about each of those as from what we just drew. And if you are pre-professional, then I recommend that you know these more at a more detailed level of what I'm about to describe, rather than just knowing like, okay, these chemical reagents only affect this part of the cell. If you know, the more you know, the better, because after all, knowledge is power, right? So surfactants affect membranes. So there's the cationic or ionic compounds here. So for cationic, those would be considered quats or quaternary compounds. They interact with phosphate groups. And then anionic. Some antimicrobial properties. So an example of the cationic or quaternary ammonium compounds would be, I have to double check my spelling on this. Cetylpyridinium and benzalconium. Okay. And so this is like the general outline that I wrote here, but now I'm going to go more in detail on the cationic or quaternary ammonium compounds. More detail. The quats attracted to cell surface. They're seen in detergents. Amphipathic. Amphi means both, so meaning that the quaternary compounds or yes, they're amphipathic, as in they have hydrophilic and hydrophobic properties. React with the phospholipids in the membranes. But unlike soaps, the quaternary compounds are not derived from fat. Usually quaternary compounds are used to clean inanimate objects, so like a tabletop. And they are ineffective against versus, that means against, ineffective against endospores, naked viruses, and mycobacteria. And so an example, or examples of the quaternary compounds are like what I wrote up here, but I'm being a little more specific: benzalkonium chloride and cetylpyridinium chloride. Okay. Next, we have the phenolics. These phenolics denature proteins, and if you denature proteins, that will affect the membrane. Because in both like eukaryotic and prokaryotic cells, there are peripheral proteins along the membrane, not just integral proteins. And the phenolics do remain active and effective. A 5% solution of containing phenolics kills bacteria. It can cause skin and neurological damage. So examples of these phenolics are Lysol. Another name for Lysol is orthophenol phenol. Triclosan. Hexachlorophene. Xylenol. So just to clarify, or more like give advice to y'all, is that as I'm going through these individually, just pay attention as to like, okay, these are effective against this. This is not effective against that. And that's why this handout's important, because like here, phenolics is considered intermediate level. So it's not effective against endospores, maybe a few subspecies of mycobacteria. And yes, phenolics will wipe out envelope viruses and fungi and other bacteria. But like the surfactants, no. Right, I said no, it won't wipe out endospores, mycobacteria, or the naked viruses. So this handout is helpful. Okay, next we talk about alcohols. So lipid solvents. Membrane lipids. Coagulate proteins. Alcohols are not effective against naked viruses, but they do kill bacteria, fungi, and enveloviruses. So not effective against naked viruses. But alcohols, but are bactericidal, fungicidal, not sporicidal. So basically, the alcohols do not wipe out endospores or naked viruses. Sporicidal, sporicidal, 70% solution. Okay. Just so you know, the suffix "cidal" means to kill or to destroy. Alcohols are used to disinfect, not sterilize surfaces. Sorry, I keep hitting this button on the pen, and it can be annoying sometimes. And then alcohols can also be used as antiseptics. An example of that would be the portable hand sanitizers. So common hand gels have 62.5% ethanol in the glycerin base. They do evaporate. Okay. The next group is the halogens. And I was checking my time. So, you know, on the periodic table, right, with, I'll show it. Periodic table. So I hope y'all know where the halogens are, but just in case you don't, I'm just pulling it up. And then, oh, and it even says halogens on there. Okay, anyway. The halogens that you can use here as chemical agents to affect the proteins in the cell are, you can use chlorine and iodine predominantly. So chlorine oxidizes cell constituents such as DNA, proteins, membranes. It can be used as a disinfectant. It can help disinfect water, dairy, food. The best thing here with chlorine is that it's cheap, easy, and effective at a low concentration, basically. Milliliters per liter, or diluting Clorox. Diluting Clorox at a rate ratio 1 to 100 to 500 parts per million. If you don't quite understand that, that's fine. I just put that in there because some of the people who love chemistry, we talked like if you took Gen Chem 1 or 2 yet, you should y'all should have talked about parts per million. But basically, I was talking about diluting Clorox, depending on the concentration of Clorox. That'll affect your final concentration once you've diluted it. But I already went through dilutions in 2 videos ago. But anyway, there's a separate video on dilutions with that. But all I'm saying is that you can use chlorine to disinfect something, or like with bleach, you normally, if the bleach is too concentrated initially, you want to add water to dilute it so it's not as strong whenever you're using it to clean. And then the other halogen here, iodine, linked as iodophore. It is mainly used as an antiseptic, like for prepping for surgery, whether it be for animals or for people. Iodine or alcohol is definitely used as an antiseptic for the doctor to be able to make a clean incision. As it says membranes. Okay. Antiseptic example, betadine, Escodine. And at the clinics I've shouted out, we've mainly used betadine to prep for surgery. The next germicidal group is the heavy metals. And the thing is with the heavy metals, they interfere with sulfur groups. S-sulfur groups in proteins. They're not as effective, but they are toxic. But I'm saying they're not as effective as the halogens. %, solution. Silver sulfidizine is used for burns. And I can speak from personal experience. If you have a 2nd degree burn, they will give you silver sulfidizine to put on that burn, on that sunburn. But, and then you have copper sulfate as an aldehyde. Okay. It basically interferes with sulfur groups in proteins. Toxic, less effective, and if you look at your handout, it's grouped as a low-level germicide. So it makes sense that it is not as effective as halogens or phenolics. So other groups of chemical agents here are peroxides. Usually you would use a 3% solution of hydrogen peroxide. And this is just a side note. Depending on your professor, you may or may not go into catalase. Catalase is basically, it is an enzyme, but you'll definitely talk about it more in biochem. my experience, usually peroxides are not really asked about a lot. It's more of biguanides, phenolics, halogens, heavy metals. Biguanides are usually used as antiseptics. An example of biguanide is chlorhexidine. If you ever volunteer at like an animal shelter, you definitely see animals, especially dogs, come in with mange, and to do that, like, you want to give them a good bath, and usually giving them multiple baths, and often we normally bathe them in chlorhexidine, at least with the really bad areas first, before adding in the soap. And aldehydes. Yes, this is important too. They inactivate proteins and DNA. And examples of aldehydes here: glutaraldehyde, and that's used to sterilize, and then formaldehyde is used to preserve, like with cadavers, or if you've ever dissected like a frog or something and you take it out of the bucket or the bag and it smells pretty strong. The smell is the formaldehyde in order to preserve the specimen or the cadaver. Or orthotaldehyde is used for high-level disinfection. So there you go. We covered a lot of ground very quickly, but if you have a lot of this, especially like with the filtration of the gases, you can look up pictures, Google it, or it'll probably be in your book if y'all are still using master. And just make sure with this last bit of which chemical agents affect which parts of the cell, make sure you know like the location of where those chemical agents affect the cell, and then those individual purposes of those chemical agents, okay? So which ones are maybe more effective at killing naked viruses, or which ones are not effective at killing envelope viruses, that kind of thing. So as you're studying, you want to be anticipating and predicting questions, especially with this. The sterilization stuff I know is not as exciting as some of these other topics, but I mean, you want to make sure if you want to clean a tabletop well, or if someone's sick and they sneeze on your table, for instance, you want to make sure that you use the right cleaning equipment so that you don't get sick, you know. And that pretty much wraps it up. So thank you and good luck studying.